Now, we're going to take up one more type of beam, which is a simply supported beam. We're going to take up simple problems on this. Problem number 11. A simply supported beam of 6 meter long is subjected to a loads of 2 kilonewton, 5 kilonewton, and 4 kilonewton at distances of 1.5 meters, 3 meters, and 4.5 meters from the left support. Draw the Sfd and Bmd. In these types of problems, the figure will not be given, so we need to write the figure. So to do that, so first we will going to have a beam of subjected to loads of 2 kilonewton, which is at a distance of 1.5 meters. So first we're going to consider a beam of 6 meters long. Since it is a simply supported, you will going to have a vertical reaction at the point A and also vertical reaction at the point B. Whose distance from here to here it is 6 meters. So point load is acting at 2 kilonewton at a distance of 1.5 meters. So from the left support. So which is the left support? This is the left support. So 2 kilonewton is acting at a distance of 1.5 meters. And then 5 kilonewton is acting at a distance of 3 meters. And 4 kilonewton, which is acting at the point E, which will be equal to 4.5 meters from the left support. So draw the Sfd and Bmd. So to do that, so first we're going to consider the reactions. So for the support reactions. So to consider the support reactions, so we're going to take the moment about the point A. So taking the moment about the point A, so we're going to have RBV into 6 because in the counterclockwise direction, and some of the counterclockwise direction will be equal to some of the clockwise direction couple. So that is RBV into 6, that will be equal to 2 into 1.5 plus 5 into 3 plus 4 into 6. So 4 into 4.5. So in other words, first we're going to take up 4 into 4.5 plus 5 into 3 plus 2 into 1.5. So load into the perpendicular distance. So on simplification, RBV will going to get it as 6 kilonewton. So also what we know is the sum of the upward reaction is equal to sum of the downward reaction. So which are all the upward reactions we have? The upward reactions we have RAV plus RBV. So then the downward reactions, which will going to be 2 plus 5 plus 4. So we know the value of RBV, which is equal to 6. So 11 minus 6, you're going to get 5 kilonewton. So RAV, reactions at the support of at A, vertical reaction at the support A, will going to be 5 kilonewton. So now we will going to consider the beam. So first we're going to start from A to C now. So here 5 kilonewton is acting upwards, and at the point C we don't consider the load now. So first, what is the shear force at the point A? Shear force at the point A to the section acting upwards is positive. So 5 kilonewton is positive. Then between A and C, as there is no load acting on the beams, therefore it remains constant at plus 5 kilonewton. So when you are considering the next, which will going to be on the shear force, you are going to get 5 kilonewton. So first SF at the point A is 5 kilonewton. Between A and C, it remains constant, which will going to be plus 5 kilonewton. So at the point C, we don't have the load now. So to that, we need to find out what will going to be the bending moment at the point A. So the bending moment at the point A is 0, and the bending moment at the point C, which will going to be again positive. So that is 5 into 1.5. So you're going to get it as 7.5 kilonewton meter, which is the positive direction. So naturally, from the bending moment at the point A is 0, and the bending moment at the point C will be plus 7.5 kilonewton meter. Now we will going to consider the point load at the point C, and also at a distance C between C and D to get till here D. But we are not considering the point load there now at this juncture. So we are taking the from left to right. I am going. So what will going to be the shear force at the point C now? So between A and C, you have got plus 5 kilonewton. Shear force at the point C will be plus 5 plus 2, which will be equal to plus 5 minus 2, which will going to be equal to plus 3 kilonewton. So when you're considering that, so naturally between C and D, as there is no other load acting on the beam, so it remains constant at plus 3 kilonewton. So this is how you will be able to get the shear force diagram. So at the point A, plus 5 kilonewton. Between A and C, it is 5 kilonewton. At the point B, it drops down to uh, 3 kilonewton, because at the point C, you are going to have plus 5 minus 2, which will be equal to plus 3 kilonewton. So between C and D, as there is no other load acting on the beam, so it remains constant at plus 3 kilonewton. Now we go for the bending moment at the point D now. So the bending moment at the point D, which will going to be, as the load is acting upwards, it tends to sag at this point. So since it is sagging, so it will going to be positive. So that will be equal to plus 5 into 3 and minus 2 into 1.5, because it hogs between C and D. So naturally minus 2 into 1.5, which will going to be equal to plus 12 kilonewton meter. So from here, so it should go to point D, which is at a distance of 12 kilonewton meter from the point A. So this is how you will be able to get the bending moment diagram for up to the point D now. Now we will go further. So when you go further, at the point D, we are considering the load of 5 kilonewton which is acting. So which will going to be SF at the point D will be equal to plus 5 into 3. Here it is a shear force diagram. So only the point loads which you need to consider. Between C and D, it remains constant at plus 3 kilonewton, and at this point D, plus 3 minus 5 will be equal to minus 2 kilonewton. So that means between D and E, it remains constant at minus 2 kilonewton. So that is how you will going to get till here, which is when you are considering the point load, it will going to drops the load from plus 3 kilonewton to minus 2 kilonewton. So then between D and E, it remains constant at minus 2 kilonewton. So between D and E, it remains constant at minus 2 kilonewton. Then at the point E, so bending moment at the point E will be equal to 5 into 4.5 minus 2 into 3 minus 5 into 1.5. So on simplification, you will going to get it as plus 9 kilonewton meter. So that means bending moment at the point E. So now we have the bending moment from plus 12 kilonewton meter. It has been drops down to plus 9 kilonewton meter. So now we will going to consider the final beam, but after E, you will going to get B. So what will going to be the shear force at the point E now? Shear force at the point E, which will be equal to, which is minus 2 minus 4, minus 2 minus 4 will be equal to minus 6 kilonewton. So from bending moment between E and B, it remains constant as there is no load acting on the beam. So it will going to remain the same as minus 6 kilonewton. So that is how you will going to get the shear force diagram, where shear force at the point E will going to be minus 6 kilonewton, because between D and E, it remains constant at minus 2. Then from since it is acting downwards, so it will going to be negative of minus 4 kilonewton. So since you are already minus 2 kilonewton, so minus 2 minus 4, it will going to become minus 6 kilonewton. Between E and B, as there is no other load acting on the beam, so it remains constant at minus 6 kilonewton. So what will going to be the bending moment at the point B? So the bending moment at the point B will be equal to 5 into 6 minus 2 into 4.5 minus 2 into 4.5 minus 5 into 3 and minus 4 into 1.5. So it will be equal to 0. So here from this point, it's going to be from 9 kilonewton meter, it drops down to 0, which is at this point, which is the bending moment diagram. So the shear force, the changes the sign at the point D. The shear force changes its sign at the point D. Therefore, you should have the maximum bending moment at this point. From the figure of the bending moment diagram, you can see that it is going to be highest of plus 12 kilonewton meter. So maximum bending moment at the point D will be equal to plus 12 kilonewton meter. So now, this is how you will be able to analyze and solve the problem on the simply supported beam with several point loads. Thank you.